9.5, testing convergence at endpoints. Essential questions. Can I find the interval of convergence for a power series? Can I determine absolute or conditional convergence? Can I identify the proper test for endpoints of an interval? These are the concepts we're going to be covering. All right, let's talk about interval of convergence. So far, we've really just been spending time on radius of convergence. Radius of convergence, and that's this. So it tells us how much from the center we go out. Now, in interval of convergence, we also need to take into account the endpoints. And so that's what we'll be doing in this lesson, taking a look at how we're going to test the endpoints. All other points outside diverge. All right, let's take an example of what we need to learn how to do. Here's a function, and we want to determine at what points it converges, what x's it converge. So far, I've only asked you what the radius of convergence is. But that's where we start. We start with the ratio test to figure out our radius of convergence. And in this case, it's going to be 4. Making it 4 will tell us, give us a hint as to what our interval of convergence will be. So this is going to be between 1 and 9. Now, what the ratio test does not tell us is what's happening at these endpoints, and that's what we want to do now. We're going to allow x to be equal to 9. And when that happens, we're going to have a series of constants, and this series is going to look like this. And it's the job of this lesson to figure out whether this converges or diverges. And in this case, it converges, and that's for in a few minutes that we'll talk about that. Now we're going to let x be the other endpoint, and when we substitute it into this power series, we're going to get this series of constants, which we recognize as a divergent series. It's the harmonic p series. All right, so ultimately, now we know a little bit more in the interval of convergence. So we know that x is going to be less than or equal to 9, but greater than 1, and does not include 1. We can also write it in interval notation and make it look like this. Okay, the ratio test is the test that gives us our radius of convergence, and there's another test that also gives you your radius of convergence, and that's called a root test, and I would like to show that to you now. But let's just show it to you with a series of constants. So what we're going to do is we're going to take a limit of the nth root of a sub n. So we're going to take the limit as n approaches infinity of the nth root of this quantity n over 2n plus 3 to the nth power. And we know that the nth power and the nth root will cancel each other out, and we end up getting this. Then we take the limit of that, and as long as it falls under the requirement of less than 1, then we say that the series converges by the root test. Now, the root test is really for to the nth power. If you don't see something to the nth power, go for the ratio test. All right, here's a power series where we can use the nth root test because you see this nth power happening here. So I'm going to take the limit as n approaches infinity of the nth root of the absolute value of x to the n over 2 to the n. Because there's an x there, we won't need to require that the a sub n term is positive. Now that's going to be equal to the limit as n approaches infinity of absolute value of x over 2. Now we want to force this to converge, so we have to put the requirement less than 1. So absolute value of x over 2 is less than 1, and we can see that the radius convergence will be equal to 2. So let's go ahead and write that out. And then multiply. And so now we know where it absolutely converges. It absolutely converges within -2 to 2. And now our job is to examine the endpoints. So we're going to allow x to be equal to 2 right in here. We're going to let it be 2. And we're going to have this. And you can see this diverges by the nth root, by the nth term test. We're going to allow it to be -2, and again it diverges by the nth term test. We're not getting the nth term to go to 0. So this is what it looks like. We are centered at 0. We know our radius of convergence is 2 on both sides, and we have examined the endpoints. So now we know that the x's between -2 and 2 converge absolutely. And we know all other x's do not. Okay, let's talk about the integral test and how it's associated with summations. It says that if the improper integral converges, then the summation of that same term will converge too. So these two terms right here. And if the improper integral diverges, then the summation of that term, that same integrand, will diverge as well. Let's take a look at the proof here. So these summations are really rectangles with a width of 1. So if the width is 1, we can regard these as the heights of the rectangle. So you can consider all of these as areas of rectangles. And so this summation is going to be less than this improper integral. And so we know if this improper integral is converging, then this will converge here, no matter where you start. You don't have to start at the first rectangle, but somewhere as you go along, then all of these will be underneath. Now, if you have an improper integral that diverges, and all of these rectangles here, we can start in such a way where all the rectangles are going to be above it, then we know that this summation will also diverge. Let's take a look at an application. So we have this summation, and it's closely associated with this integral, 1 over, and then we're going to convert this to x. So this is x root x dx. So whatever the improper integral does, the summation will do as well. And so we go ahead and find the value of the improper integral, and we find that it's 2. And that tells us the improper integral converges, so that tells us the summation converges as well. Now this is closely associated with the p-series. The p-series also is being proved whether it converges or diverges through the integral test. And when p is equal to 1, we know that as the harmonic series. And we've done this before, and we know that is going to diverge. And here's some examples of p-series. When the exponent, the p, is less than 1, then we know it diverges. And we know when p is greater than 1, it converges.